So, good afternoon. Let us wait for a minute or two, or else we'll start. Did you have any problem solving the assignment? Any one of you had any doubts in the assignment? We can discuss it now. So, these live lectures are basically for solving doubts and discussing any problems that you're facing in the assignments or the coursework. So today I was thinking that I'll solve or explain one problem that involves both projection of solids and the auxiliary plane, and then I'll go through some problems of the last time's assignment, like the week 6 assignment problems. I will cover in this lecture. So I think we should start. Whoever will join, let them join. So, welcome to the live lecture for Engineering Drawing and Computer Graphics course. So, this course is being conducted by Professor Rajaram Lakkaraju from IIT Kharagpur, and today this live lecture is conducted by me, Sanika. I am a PhD scholar in Indian Institute of Science, Bangalore. So, like I said, we will solve one problem that involves both solids and auxiliary planes, and then I will go through the problems from the week 6 assignment. So, this is the problem. Let us first just read the problem and try to understand it. So, a tetrahedron which has 60 edge. So, that means what is a tetrahedron? It has four sides, four of which are triangles. So this figure here is a tetrahedron. What is given is it has 60 edge. So all these sides 1, 2, 3, 4, 5, and 6 all are equal to 60 which rests on a face of its ground of it on the ground. So that means the triangle is on the horizontal plane. That is, it is flat on the ground, and an edge of its face is inclined to the vertical plane at 45. So it is inclined to vertical plane. This will be visible in the horizontal plane. Now they have given that. One second, I'll just add. Okay, so now they have given that there is a sphere which is of 70 diameter placed on the ground and touches the face of the tetrahedron. So imagine we have a sphere here, somewhere like this, which is touching this face and is placed on the ground. So, if you have, so this is not a tetrahedron, but it is similar to it. So, consider that this is one surface and consider that this is a ball. So, it is resting like this here. Can you imagine from the problem? So, this is the case that they are explaining. So, what they have said is the sphere is placed on the ground and touches the face of the tetrahedron containing the said edge centrally. That means centrally means it is on this line, like it is at the center. It is symmetric to this triangle. So they have asked us to draw the projection of the tetrahedron and the sphere. So let us first start the projection of a tetrahedron. So, So this is a tetrahedron that I have shown here, this one. So let us start with top view. So in top view, we will see the tetrahedron as a, what will we see in top view? We will see a equilateral triangle like this. So this equilateral triangle could be in this way, it could be this way, whichever way you want it. So this triangle is this base, and these three planes will be visible. I'll show how. So I'll draw lines here. So these the three edges will be visible like this. One, two, and three. Okay. So uh, so let us name the edges now, or I'll name them as A, B, and C, and let this point be O. So if you see here, I have marked this as A, this as B, and this as C, and this top as O. Now, what they have told us is that one of its edges is inclined to VP. So one of the edge is inclined to VP. So let us say that we have this edge AB inclined to vertical plane. So if this is the vertical plane and am making an angle 45 with the vertical plane, where will I see it? I'll see it in the top view. So that is, I'll see it here. So I'll now actually rotate all of this so that uh, first group that. Okay, so I can now rotate this such that this edge AB makes an angle of 45 with the horizontal plane. So we'll have to rename it. I'll take these off. Oh, let me see. So I will now rotate it such that this line AB will make 45 with the vertical plane like this. This should be 45 degrees. So I'll rotate this thing. I'll rotate it like this. So this approximately will make an angle of 45 with the vertical plane. This is point O. So if if I draw a horizontal line over here, then this angle is 45 degrees. Okay. So this was our top view. Now when we look at the front view like this, we need to know the elevation of point O from the base. How do we determine that? Like what do we know? We know this true length is 60 mm. Do we know what angle this is making with the horizontal? We don't know. Like how do you imagine you can determine this height, this particular height? So I'll take these off. So I want to determine the height of point O from the base, because that is what we'll see in the front view. So when we only know this is the true length 60 mm, but we do not know its elevation angle with any of the planes. So we will think like this: when do we see the true length of any line? When will we see the true length of any line? We will see it when that line is parallel to one of the projection planes. So if this line OC is parallel to VP, I'll see the original or the true length in the vertical plane. So like I have explained before also, uh, we see the true length when the plane we'll see the true length in vertical plane if the plane is perpendicular to the horizontal plane and it passes through the line whose true length we want to see. So here what we will do, before we used to rotate this projection. We used to rotate this projection so that OC becomes parallel to the uh, VP. But instead of doing that, we can also have auxiliary planes. So instead of rotating OC this time, instead of rotating OC and getting it parallel to VP, what I'll do, I'll keep OC like this and I'll have a auxiliary vertical plane which has, this was the original vertical plane, this is OC. So I will rotate this vertical plane so that it becomes parallel to OC. So that becomes the auxiliary vertical plane and it is already perpendicular to the horizontal plane. So in this plane, I should see original length of OC. So let us go ahead and draw this auxiliary plane x1, y1. So I will draw a auxiliary plane which is parallel to OC. I will draw it slightly here. I'll move this. Okay. So, so this is our auxiliary plane. I can actually move it still further because the next projection that we are going to draw will come exactly above this. Okay, so right now this line is my auxiliary plane x1 y1, which is parallel to the line, okay, which is parallel to the line OC. So this is x1 y1. So x1 y1 is parallel to OC, this one. Okay. So if we if we have a vertical plane here and we have rotated it, so you will see it is still perpendicular to HP. So you will see it as a line in the horizontal plane, and uh, you will, yeah, so you will see it as a horizontal line in the horizontal plane. So this is your auxiliary plane, which is still perpendicular to HP. So I had this line OC like this. OC is like this, and I have constructed a plane that is now parallel to this line OC. Okay, so this will be my horizontal plane, and this will be my vertical plane. So now here this is parallel to this. So if I draw a a perpendicular from point O to xy and extend it further. So this particular drawing is still in the horizontal plane. I have just made a plane that is that is parallel to OC. So I'll drop a perpendicular from O to x1 y1, and we'll show it by a dashed line. We'll show it by a dashed line. Similarly, I can drop a perpendicular from the point C, and also I can draw a perpendicular from this A, and we will also coincide with that line. So now in this plane which is parallel to OC, so initially my vertical plane was like this, my horizontal plane was like this, my vertical plane has now become like this. So will the projection of the height of this O change? No, it will not change in vertical plane. What has changed is it's equivalent to rotating this top view. So taking this one, instead of taking this one and rotating it, what I've done, I've just placed a plane x1 y1 which is rotated. So now here, this is my top view, and I'll draw the auxiliary front view. So what I know is, I still don't know the height, but what I know is that this line OC will be seen as a true length in the vertical plane. So uh, on this line O will lie, and on this line C will lie. So I know that length length of OC is this. Okay, and I know the hypotenuse, which is the side OC, which is equal to 60 mm. So in front view, it is as good as saying that I know one side of the right angle triangle and the hypotenuse. So I will construct this OC over here. So I'll draw OC. So OC will be like this. So this is the front view. So since the base is on the horizontal plane, the all the points A, B, and C will appear in a single line uh, a single line. So this will not be O. This will be, let us say, some center point D. So this is D, which is the projection of O, which is the projection of this point O on ABC. So
ಅಂದ್ರೆ ಇದು ಗೂಗಲ್ ಮೀಟ್ ಅವರು ಕಾಲ್ ಇದ್ ಕರೆದಿರ್ತಾರಲ್ಲ ಮೀಟಿಂಗ್ದು. ಹಲೋ ಹಲೋ ಅರ್ಜುನ್, ಕೇಳಿಸ್ತಾ ಆಯ್ತಾ? 3:05ಕ್ಕೆ ಜಾಯಿನ್ ಆಗೋದಕ್ಕೆ ಟ್ರೈ.
so this is my point C, and this is my point D. So I have drawn this line CD. Okay, so this is the projection of OC actually. And now if I take the rounder and have 60 length in the rounder, and I mark from C to intersect this dashed line, I will get the uh, height of point O. So let us draw such a line there. This line will start from here, and the length of line should be 60 and it should make an arc that this line intersects with this line. So with wherever it will intersect, that will be our point O in the front view. Now, once this tetrahedron is placed on the HP, from wherever I view, until and unless I do not tilt its base, this O height will remain same. It will uh, remain unchanged. So, this height O I have got now, and I will. And if I draw another line here, that will be my AB points, and this line this line will represent OB and OA. So I will construct these lines here. So you can see that this line will the length of this line will not be 60. The line OB and OA will not appear as 60 in this view because OA and OB are not parallel to the vertical plane. Only OC is parallel to vertical plane, and when it is parallel, only then we'll see the true length. So this is 60 mm, but OB and OC that we see here, they are less than 60 mm. They are they are not the true lengths of OA and OB. So now from here what do we get? We get the height of the tetrahedron, which we can see in the front view. Okay, so now we can construct the front view. So from the auxiliary plane view, what did we get? We got the height. Now measuring the same height OD. Now measuring the same height OD, we can draw the front view here. So similarly, if I draw the projections from here, so I'll project this point B in the vertical plane like this. I'll change the color for this line so that it does not become confusing. Uh, where is it? Okay, so I'll make it yellow, and then I'll project point O. Oh wait. Then I'll project point O, and I'll project point A. I'll project point A in the vertical plane, and I'll project point C in the vertical plane. Now they haven't. What they have mentioned is the base is on the horizontal plane. So what is the distance from the horizontal plane? 0. What does it mean in the vertical plane when we see the base ABC will be? Where will the base be? The base will be on XY itself here. So I will draw first the base AB. We will take a line and I'll draw the base AB here. And since okay, so this is I'm sorry, base ABC, not AB. So we know that all the 3 points A, B, and C are in the horizontal plane. So this point will be C, this point will be B, this point will be A. And now O, for O, we need to get the height from here. Okay, so I will, what I'll do, I'll draw a line here. I'll draw a line here like this. And I'll move that line. So this you will, in actual drawings, you will be doing it with, by taking the distance in the rounders. Here, I can do it easily in PowerPoint. So let us rotate this line. Let us rotate this line by, let's, I think 45 should do. Huh? So let us rotate this line so that now this is vertical. So I have, what I've done, I measured this length OD. I measured this length OD and I projected it here. But where should that line be? So this height is from where? It is from the base to O. So where does the point O lie? It lies on this line. It lies on this projected line. And the height is this O. So now when I join, OA, I will have projection of I'm sorry. When I join OC, I will have projection of this line OC as this. When I join OB, when I join O and this point B, I'll have projection of which line? I'll have projection of this one. And when I join point O and this point, which is the projection of, so this line, uh, this line is the projection of point A here. So when I join O and this line, because this is the line where where the base plane lies, that's why ABC lie on this plane, and I'm joining OA, OB and OC. So now if we see this line OA will be actually a invisible line, which will be a dotted dashed line. So I will make it as dashed line. So that will appear as a dashed line. So now I will rename it properly. Mm, So this was my point O. This line is projection of line point C. So this is OC. This line, is projection of point A. So this is OA. This is projection of point O. This is point O, and this is projection of B. So this is B, and this was A. So now we have the projection of tetrahedron. Now let us move on to the next part of the problem, where they have said that there is a, so I'll just rename these O, A and B. Yeah. So now what they have said is there is a sphere of 70 mm diameter which is placed on the ground. So if this is my tetrahedron, this is actually a square pyramid, but assume that this is one face of the tetrahedron, then they have said that they have a sphere which rests on this surface and it rests on the ground. But how is this face oriented? This face is oriented like this at 45 to the vertical plane. So the ball is here in front somewhere. So they have asked us to draw the projection of this ball such that it touches the face and the ground. Now, what do we need to think is, if this is the ball, when can we see the, if this is the ball, this is like one inclined plane and this is like another inclined plane. This is the horizontal plane. So assume that this is the horizontal plane and we have this as the inclined plane here. And now imagine that I have a ball placed in front of this. So when you're looking at this, when I have a plane that passes through the center of the sphere, what I will see? I will see a circle like this, the radius perpendicular to this plane and a radius perpendicular to this plane. So let us try to draw that figure first. Okay, so I have this horizontal plane, and this will be some inclined plane which is right now the surface of our tetrahedron. And if I am drawing this projection in a plane that is passing through the center of the circle, I will see something like this. So I have a circle like this. All right. Now this is touching the ground. So the position of circle will be like this. So here you should note that at any time, at all points, in any case, the center of the sphere, the center of the sphere will always be 35 mm from the ground. Why? Because they have given diameter as 75 mm, so radius is 35 mm. So anyhow, if we keep the sphere like this, like this, like this, it is symmetric. So in whichever case, this center point of the sphere will be 35 mm above the ground. And now they have said that if these are the two planes, the sphere is also touching this inclined surface. So I will shift this circle here so that it touches the inclined face. So if you have this, if you have this, then this was my center. I have this as radius 35, and this will also be perpendicular to this thing because this is like a tangent. This inclined plane will be tangent to the circle or the sphere. So this will also be a perpendicular. Now we already know that if such a case is there, this point will lie on the angle bisector of this angle. So we have already covered this in previous lectures that this point is on the angle bisector. So this was true when we knew the true angle between the planes. Otherwise, if we have the planes like this, now you are seeing the true angle. If I rotate it like this, you will first of all see the projection of a plane as a parallelogram, this plane also as a parallelogram, and somewhere here in middle, this circle will come and touch. So here, when you see it like this, you just see it along the length. You don't see where it is on the width. Okay, but you can uh, draw this angle bisector only when you know the true angle. So when do we know the true angle between two planes? We can know the true angle only if we have a plane that is perpendicular to both the planes. So if I take this particular thing, the plane perpendicular to this horizontal plane will be any plane which can rotate like this, and a plane that will also be perpendicular to this will be a plane like this. So now let us go to our problem. So here, what is the case? This is my tetrahedron face, and this is my horizontal plane, and I have a sphere like this over here. Okay, so what do I need to see? I want to see the actual true angle between this face and the horizontal plane. Okay, when will I have that? When, so which face do I want as in between which two faces do I want the true angle? I want it between this face and the horizontal plane. So what does that mean? I want a plane that is perpendicular to the horizontal plane and perpendicular to this plane OAB. Okay, so if a plane, if any plane is perpendicular to the projection planes, Okay, so assume that this is my plane and I'm projecting it on this vertical plane. So when will I see the, if it is perpendicular to the projection plane, I will see the projection of this plane as a single line. Alright, so when I am when I'm looking at this auxiliary projection, luckily we have got that this plane AB, this plane AB is being observed as a single line. If we had an auxiliary plane at a angle like this, maybe like this, then we would have seen two triangles over here. Like we should have projected it here, here, and we will see some skewed triangles, one here, and one behind, something like this. But right now, but right now, we can see the plane OAB as a line here. OA and OB are coinciding, and we can see this plane as a line in this view. So, in order to have a plane which is in order to have a plane which is perpendicular to the horizontal plane, so I have the face of the tetrahedron like this right now, like this. It is slightly facing towards U. So if I want a plane which is perpendicular to HP, so vertical plane, which we have a vertical plane here, that is already perpendicular to HP. So I'll just have to rotate that vertical plane so that it is perpendicular to this face. So that it is, so we are constructing a auxiliary vertical plane. Now this is perpendicular like this. When will it be perpendicular? In that perpendicular view, I'll see the plane OAB as a line. So luckily we have got that the same x1 y1 that we constructed to get the height of the tetrahedron, we that same plane is also a plane which is perpendicular to HP and this plane OAB. Okay, so now we, like I explained here, if this is my plane and I have a sphere sitting here, I could see the I could see the center of the sphere on the angle bisector of this angle, because this was what I was seeing was a true angle. So now I have rotated this in the now I have taken this auxiliary plane view where I can see the true angle of this plane OAB with the horizontal plane. So this is my inclined plane and this is my horizontal plane. So the center of my sphere will lie on the angle bisector of this angle OA, and let us name this as maybe N. Okay, so let us just draw the angle bisector. Anyone is having any doubts till now? You can speak up, like even any small doubt you have, it will clear many of your understandings. So, yes,
Uh, while calculating, while finding the true length of the tetrahedron, so instead of making the plane inclined x1 y1 at 45 degree, we can calculate the height directly from the top view. Na? If we draw a horizontal line from O and then we rotate OC, edge OC around
yes,
O.
yes, you are correct. You can do that also. But for that, only thing you need to do is you have to again draw that ABC triangle separately in the top view, then get the height. You can do that also. See, auxiliary plane is actually the same thing. You are either rotating the top view or you are rotating the XY plane so that the top view gets oriented correctly.
Okay, ma'am. Okay.
Yeah, you are correct. We could have done that also, but here we were trying to learn the auxiliary plane concept. So I showed you how you can do it with auxiliary plane. In fact, I was going to say that instead of doing all this construction, you can simply rotate the top view, so that this OC becomes parallel to the original XY, and then you can get the height. So now for the sphere thing, now I'm going to draw this angle bisector. So this is the angle bisector here, and I know that the center of the sphere is 35 mm above HP. So that distance, that above HP distance will be seen in the vertical plane. So I'll draw a line which is 35 mm, which is 35 mm from HP. So this is my line which is 35 mm above HP. So the center of the sphere, as we can see it uh, in this view, where we can see the true angle between the planes, the horizontal plane and angle OAB. I see it here. So it lies on the angle bisector of this angle, and it lies 35 mm above. So I will get the center of the sphere as this point. I'll get the center as this point here. So now if I go and draw a circle, so from this as center, if I draw a circle, uh, draw a circle like this, which it is a lot easier to actually draw circles in your original drawings. Okay, so the radius should be 35, which is equal to the uh, height from here. So this should be 35, and this will be 35 anyways, because that is how you have constructed the center of the circle. So now once you get this circle, now when you look from the top view, if this is the face, the center of circle could be anywhere, like it could have been anywhere along this line, here, anywhere, but only in the front view, when you're looking at a particular front view where you see the triangle, you can locate the exact center. So now to locate the center, now you will drop a perpendicular from this obtained uh, location of the center of the circle. So I'll drop a perpendicular from this point, and I'm going to change the color because this is now the third projection that we are drawing here. Okay, so I will keep it as green. Okay, so wherever this intersects this line, because they have said that the circle touches it centrally, so it is at the center of this plane. So if you draw a line like this which bisects this angle, then the circle will then it touches somewhere on this line. So that's why I have drawn this line, and wherever the projection of O touches this line, that will be the center of the circle. Now, since it is a sphere, whether you view it from top side, anywhere you view it, it will be the same circle with diameter as 35. So this is slightly off actually. So I will copy this circle 70 diameter and I'll place it here such that this is the center and diameter is 70 or radius is 35. So this is my O. And if you will see, I will also be able to determine this point by dropping a projection from here on this line. So this point and this should be in one line for this x1 y1 auxiliary plane. So now you got the projection of the circle here. Now you can project this center in the original xy plane. So I will now project the obtained O in our required plane, in the xy plane, in the VP of the xy plane. So this is the fourth projection that we are taking, and I'll make it as orange for clarity. So this is where my O point will lie. And second, I know that it will be 35 above the HP. So again, I can draw a line which is 35 from this xy, is 35 from this xy, and it will lie on this orange line. So similarly, I can draw the same circle with same radius. Because it is a sphere, it will look same. Okay, so uh, so this was my center of the circle. And actually all so till here you will see the actual circle, and after this you should be seeing a dotted line because the circle has gone behind the triangle. And since it is coming out uh, from here, this will again be a solid line, this will be a solid line, and this part will be dotted line. So that is how you can solve any problems. So finally, even if it is a solid or a plane, you always need to remember some few basic things. You can imagine a plane using lines. So if it is a rectangle plane, you have this line, this line, this line, and this line. And with respect to these lines, you can construct the plane. If you have a 3D object, with respect to plane and lines, you can construct the whole object. One thing you need to remember is true length is visible always when we have true length of a line is visible when the line is parallel to that plane. And true length of a plane or true angle of a plane will be visible when there is in which plane will the true angle or true projection of the plane will be visible when the third plane in which we are projecting it is perpendicular to both the planes. So all you need to think about is when you can see the true length, and if you know the true length, then you can orient your object such that you can see the true length, construct it, and go ahead. So like you were saying that instead of drawing this auxiliary view, you could have also done you could have rotated this view like this, so that OC becomes parallel. So now instead of constructing it this here at an angle, only thing I would have done is I would have constructed it in this plane. So I will have one figure where I have it tilted at 45. There will be a second figure where I have OC parallel to the XY plane. Then I get the height. Then in third figure, I'll have this construction of the circle and everything. So auxiliary planes and that thing is similar thing. It is similar to saying that either the observer is moving from here to here or we are rotating the object. It's finally the same thing. It is just how you imagine it and how you can draw it so that others understand it, like easiness of or clarity of drawing. So that is all you use all these different kind of things. Okay, so do you have any doubts in the assignment problem? I'm going to go through them very quickly. Okay, so let us go through the assignment problem. So we have a regular tetrahedron which is placed on a horizontal plane of its base. So this is similar to the problem that we did now. So how will it look in front view, top view, and side view? So tetrahedron, like I mentioned before, it has four sides. All of them are uh, triangles. All right. So this is a tetrahedron, and we have it placed on the horizontal plane. One of the base is on the horizontal plane. Now, the in top view we can see a equilateral triangle like this, like this, like this, and anyhow. So in front view, in this case, if this line is parallel to VP, I will see a triangle like this, two triangles. In top view, I will see a triangle. In front view, I will see two triangles. In this case also, I will have a similar thing, but this line will be a dashed line. If I have like this, and in side view, if I'm viewing from this side, since this is parallel to VP, I will see it as a, in side view, I will see it as a, how will I say it? This will be a triangle, and my both points, this point and this point will coincide over here, and the third line will be here. So in that case, I'll see only one triangle in side view, two triangles in front view, and one triangle in top view. If I rotate it slightly like this, so this is no side is parallel to any side. Then in uh, then in I'll just change the color then. Yeah. So then in front view, here, here, and here, you will see two triangles like this. One triangle is this, one triangle is this, and the third triangle will be obviously this. And also in side view, if you project it here, you will again see two triangles, and in top view, one triangle. So it depends how your tetrahedron is placed, whether you will see one triangle or two triangles in either top view or side view. Sorry, in front view or side view. So the next problem was when the plane surface is held with its surface parallel to one of its planes of projection, the view of the plane surface projected on it will be. So like I said, if you have a plane which is parallel to another plane, the projection will give you the true length or the actual uh, shape of the plane. So if this is our plane, this is our plane and it is parallel to here HP. So we will get the true shape of that plane projected on the projection plane. Third is when the plane is perpendicular to both HP and VP, its front view will be. So when the plane is perpendicular to both HP and VP, this is my VP and this is my HP. So in this case, in front view I will see a line. If it was only perpendicular to HP, then uh, nothing is said about angle with VP. Then I'll actually start with this thing. As I rotate this, so like this plane, if it is like this, I will see projection as this. As I rotate this plane like this, I will see smaller and smaller rectangles it will come down to a line, and again when I go further here, I will again start seeing bigger and bigger rectangles until I reach parallel to VP. If I rotate further, again I'll be able to see smaller and smaller rectangles. So the true shape of an oblique plane is obtained in. So like in a line, we said that again the same thing. You see the true length only when it is parallel to some plane. So if the plane is at an angle with both the HP and VP, we will not see the true length in any of the projections. So the correct answer is none. So here also, if I rotate this plane, if I rotate this plane so that it becomes uh, perpendicular to HP and at an angle to VP, then here I will see the true length in HP. Or if I rotate it like this, I'll see the true length in VP. Okay, so a line of length 20 centimeter lies on a profile plane whose ends are at a distance of 5 centimeter and 7 centimeter to the horizontal plane. What is the length of front view? So these two problems actually have same concept. So the line lies in profile plane and ends are 5 centimeter from the horizontal plane. So one end is here, this will be one locus, and this will be another locus. So this is 5 centimeter and this distance is 7 centimeter from the horizontal plane. So I have like the height of the triangle, and I know that the true length is 20 centimeters. So since it lies in the profile plane, I will see the true length. So this is again equal to, I have one side of the right angle triangle and I have the hypotenuse. So I can mark 20 here. So I will get the two ends of the line. So let us name them as A and B. And what they've asked is, what is the length in front view? So you need not actually construct this line in front view. What you will see is this difference. So the difference is 7 minus 5, which is equal to 2 centimeters. Now similarly, a line LM lies on a profile plane and horizontal plane. Line LM lies on the profile plane and the horizontal plane. So which means that the line is here. Okay, so then which of the following two views coincide to give a line again? So this is my profile plane, which I see side view. This is my front view on the vertical plane. This is my top view in the horizontal plane. So I will see the line in side view and top view. So answer is side view and top view. So the next problem is a line which is parallel to the vertical plane and makes an angle 30 degrees with the horizontal has a length of 5 centimeter in side view. What is its true length? So the line is parallel to the vertical plane, which means it can be like this, like this, like this, like this, anyhow. And it makes an angle 30 degrees with the horizontal. So that means the line is like this and it makes 30 degrees with the horizontal. We have not been told anything about the end, so we'll just assume that it is somewhere above HP. And it has length of 5 centimeter in side view. So in side view, I'll see this length, which is equal to the length of the line sine 30. So then what is the true length? So L sine 30 is 5 centimeters. So L will be 5 by sine 30. So you can easily calculate that. And the last problem is a point is 2 units away from the vertical plane, 2 units away from the vertical plane, 3 units away from the profile plane, and 7 units away from the horizontal plane. What are the projections? So, what they've given is 2 units away from the vertical plane. So, this is the vertical plane. So, if we construct a plane here like this, which is 2 units away, the point lies anywhere on this plane. And this distance is 2 units. Then they have said 3 units away from the profile plane. So I can draw another plane here. So this is 3 units. So wherever this plane and this plane will intersect, somewhere here, if I draw parallel to this, so this they'll intersect here, and 7 units away from the horizontal. So 7 mm above. So 7 mm above the plane. So then finally you have the point is here, somewhere here. So this distance will be 2, this will be 3, and this is 7. So this is our point A. So distance between front view and the side view are. So front view is this is my side view. So when we project it on a paper, when we project it on a paper, we have it like this. So this will be the front view, this will be my side view. So I'll have 2 plus 3, that is equal to 5 units. So that's it for today. Uh, so the session starts at 3 o'clock and ends at 4 o'clock. But I think you've joined for the first time. So if you have any doubts, Sagar, you can ask me. But next time, please try to join the session at 3 o'clock. Anyway, I will be uploading this session on YouTube, so you can watch it later also. But if you have any doubts, you can ask. You were saying something? Sagar, were you trying to say something? If someone is not able to speak, also, you can put your doubts in the chat messages also. So once I finish my presentation, I can go there and look at the questions. So did you understand whatever I explained right now? Whoever was there for the complete lecture?
Yes, ma'am. We understood.
Okay,
Yes,
so
ma'am. Yes, ma'am. Understood.
okay, so like how are you finding the assignment questions? Are they easy, difficult? Are you able to imagine the objects?
Yeah, ma'am. Out of 10 question, 5 questions are okay. They are
Hmm.
easy,
Hmm.
but remain 4 to 5 questions are required to work on it. And requires some, we need to draw some figure and something.
So, but are you able to draw it? Like,
Yeah, ma'am. Yeah,
huh.
yeah.
Hmm. Okay. So next lecture, what should we cover? Like, do you have any particular things that you were not able to understand? We can maybe try to cover that.
Yes, ma'am. What?
I was saying that if there are any particular things that you want me to cover in the next lecture, like any particular problem that you did not understand or something like that.
So can we post later on?
Yes, yes. So actually, if you posted on that discussion forum, I won't get the messages. So maybe you can either post it in the YouTube comments or you can mail me with your
Okay,
questions.
ma'am. Okay. Okay.
Okay. So thank you for joining the lecture. We'll meet on next Saturday, 3 to 4. So, before coming to the lecture, you try to have some doubts. So, we will first solve the doubts and then we'll continue with the presentation that I have prepared. Okay, so,
Okay. Thank you, ma'am.
okay. So, let us stop for today.
Thank you, ma'am. Bye.
Okay, bye.